let's maybe talk about the field a bit more. So since we now know the field, we know how to add these numbers, we know how to multiply them, we have some idea what it means. We're going to talk about some metric properties in a second, but let me just talk a bit more generally about the field. So in England, for historical reasons, we learn complex analysis in the second year of undergraduate, and it's supposed, at least if you're doing a degree in maths, at least that was the way it worked in my day. And it's quite an advanced subject, as you know, this is a graduate course here in America. So most students don't understand it very well, and I was certainly one of them. And one of the things I found off-putting about this subject, and this might sound ridiculous, was that I didn't like that we had to deal with I, which was the square root of -1. So like the 15th century mathematicians, whatever, to me this seemed a bit odd. The whole thing just seemed odd for exactly this reason, that we're working in this set of numbers which weren't real, that didn't have a meaning in the real world. So I was a little bit kind of skeptical of the whole subject to begin with, and kind of speaks to my lack of mathematical maturity, age 19. But nevertheless, if you are like me, well, I have to confess, this was in my mind for actually a long time afterwards, that all of this stuff is about something that doesn't exist. Square root of -1 doesn't exist. So it was sometime later that it was pointed out to me, I saw somewhere, that we don't actually have to deal with square root of -1. We don't have to deal with complex numbers at all to do complex analysis, because of the following thing, that if we just step back for a second, what we're dealing with here is a field of numbers, two-dimensional field, where we can add them and multiply them in nice ways. And here's another field that we can add and multiply in nice ways. In fact, I'm going to show you it's exactly the same. It's going to do exactly the same thing as complex numbers. So I'm going to define the conformal matrices, which is something we're going to need later on anyway. So conformal matrices, this set. So it's a set of 2 by 2 matrices of this form: A minus B, B, A, where A and B are real numbers. Okay, that's the conformal matrices. So this is the same as the set of all lambda times a rotation matrix, which I'll write as R of theta. So where theta is any real number, and R of theta is cosine of theta minus sine of theta, sine of theta, cosine of theta. Okay, so this thing I claim is a field, and it has all the properties that we want. So we can certainly add numbers, right? Or we can add elements of this field. So if we have, say, A and B belonging to these conformal matrices, I call it A and B. Let's call it A1 and A2. So A1 and A2. Then A1 is, say, A1 minus B1, B1, A1, A2, A2 minus B2, B2, A2, and we know how to add matrices. So A1 plus A2 is A1 plus A2 minus B1 plus B2, B1 plus B2, A1 plus A2, which itself is a conformal matrix, right? So we can add conformal matrices. We're back in the space of conformal matrices, That's not a surprise. Probably not also a surprise that if we multiply these two guys, something similar happens. Then we have A1 minus B1, B1, A1, A2 minus B2, B2, A2. And we know how to multiply matrices. That's well defined, right? So what we get, this column times this column, we're going to have A1, A2 plus or minus B1, B2. We're taking this column, acting on this row to get the first entry. We know how to do this, right? Then we're going to have A2, B1 plus A1, B2, this column acting on this row, then this column acting on this row. We are going to have minus B2, A1, minus B1, A2. And then finally, this thing acting on this thing, we are going to have minus B1, B2 plus A1, A2. Yeah? And sure enough, this is a conformal matrix again. This is the same as this. And this guy is minus this guy. Yeah? So with multiplication, these conformal matrices are all good. We multiply them together. We're back in the conformal matrices. What is also cool about this is that this is commutative. So multiplying matrices normally is not commutative. This thing is commutative. Okay, and you can kind of see that because what we're actually doing is multiplying rotations times a dilation, because these things are just rotations times a dilation. And you should know that if you multiply rotations, you can do that in any order, right? So if you have two rotations, you rotate the first one, then the second one, that's the same as rotating the second one and the first one. Yeah? Yeah? So this is actually commutative. It's an algebraic fact, but from the fact that we know this is basically, or this is exactly a dilation times a rotation, it shouldn't be a surprise that this thing is the same as this thing. So we actually have a commutative operation of multiplication on this two-dimensional field. Yeah? Cool. And what else? Well, let's just write this. Let's write A, B with a bracket and a little c. Let's take that notation to mean this. Okay. Then, what do we know? Then we have that A1, B1 is A1 plus A2, B1 plus B2. See, that's the first thing we just did over there. And then this thing tells us that if we multiply these things, A1, A2, A1, B1, A2, B2, then this thing is A1, A2 minus B1, B2, A1, or A2, B1, plus, it should be A1 right here, A1, B2. Okay? That's what this second line tells us just here. And in fact, what is this telling us? This is telling us that the operations of addition and multiplication are doing exactly the same thing as the complex numbers. Because when we multiply complex numbers, A1 plus IB1, A2 plus IB2, we get exactly this stuff right here. Yeah? Yeah? You see what I mean? So what we actually have is a field that behaves in exactly the same way as the complex numbers. If we make this identification of A plus IB is like the conformal matrix defined by this AB, then every single step of every proof we will do will be exactly the same, because these operations are exactly the same. They're doing exactly the same thing. So if we, instead of doing calculus from the complex plane to the complex plane, we decide to do calculus from the conformal matrices, which is a nice two-dimensional linear space. So we consider the space of functions from the conformal matrices to the conformal matrices, and we try and develop the calculus of that, what we will have is a completely identical theory to the theory of complex numbers. Yeah? And in fact, morally speaking, these things are exactly the same. These things are exactly the same. So we're not developing an identical theory, we're developing the same theory. Because all we care about, all we're doing is we have a two-dimensional field that has these nice algebraic operations of addition and multiplication. And those operations are identical for the complex numbers and for the conformal matrices. Okay? So if, like me, age 19 and quite a number of years later, you were kind of skeptical about this subject because you didn't like I, you didn't like square root of -1, there's no need to actually have square root of -1 in this course. I could just never mention it. I could not mention it at the beginning and never mention it ever because it's not needed here. It's not needed here. No? All that is needed is we have a field with these nice operations that behave in this way, and then we develop the entire theory this way. Yeah? So for me, conformal matrices, rotations times the dilation, are actually a more natural thing. You can see them in the real world than complex numbers, but actually they're exactly the same thing. They're exactly the same thing. Okay? But for traditional reasons, we're not going to do that. We're actually going to do things with complex numbers, but just keep in mind that it is nothing more than a kind of notational convenience to have something like this. The real important thing is these algebraic operations that follow from defining I to be the square root of -1, so that in particular when we multiply I by itself, we get -1. Yeah? That's the property that defines this multiplication operation. Yeah? But it's not an essential feature of what we're about to do. Yeah? So think of this as just a very convenient notation, and it is an extremely convenient notation to deal with this. So in my own work, I'm often using this notation even when doing things in the which are not to do with complex analysis, that are real analysis, because this notation is incredibly convenient in lots of ways. So this is more notation than an actual real thing.